Yellowstone supervolcano's rock record rolling through much of Earth's time. These are the latest caldera chronicles. They come out every Monday. This is February 3rd's issue. Yellowstone Caldera Chronicles, a weekly column written by scientists and collaborators of Yellowstone Volcano Observatory. This week's contribution is from Laura Blackstone, Yellowstone Geology Program guest scientist, and Jefferson Hungerford, park geologist at the Yellowstone Center for Resource in Yellowstone National Park. Many people understand that Yellowstone National Park is unique because it hosts more than half of Earth's geysers, actually 60% of Earth's geysers, mud pots and thermal springs, and it has over 10,000 hydrothermal areas. The park is also unique because it contains rock formations that span over half of the Earth's 4.6 billion year lifespan. These rock formations tell stories of sinking, pulling, contracting, and twisting of an ever-changing landscape. In Paleozoic era, 542 to 251 million years ago, sea levels rose and fell, while Yellowstone area was close to the equator. Can you believe that? Kindly support my Patreon account since YouTube has again demonetized my YouTube channel. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. This area, at that time, was close to the equator due to the ever-shifting nature of Earth's tectonic plates. Layers of limestone, shale, and sandstone record of periods of deposition in shallow marine environments like the present-day Bahamas and U.S. East Coast. These rocks can be seen in the mountains of the Gallatin Range on the western border of the park. During the Mesozoic era, 251 to 66 million years ago, the North American continental plate gradually moved from the equator to approximately where it is now. At the beginning of the Mesozoic era, the subduction zone was present along the west coast of North America as two tectonic plates collided and one dove beneath the other. The compression on the North American plate and melting that resulted from this subduction resulted in volcanism like we see in the Cascade Range today, and the pushing up of mountains to the west of Yellowstone's region. During the early to middle parts of the Mesozoic era, the Yellowstone region reverted back and forth between a coastal plain and a shallow sea. Over time, the compression of the North American plate pushed the mountain building farther east towards the Yellowstone region. The sedimentary rock layers throughout western North America began faulting and folding in what geologists call the severe orogeny. Orogeny means mountain building from the compression of Earth's crust, which lasted for about 140 to 50 million years ago. Much of what you see in the Rocky Mountains, which includes the Gallatin Range in the northwestern part of the park, is a result of the mountain building. Late in the Mesozoic era, sea levels rose again and the Yellowstone region became part of a shallow sea at the foot of the mountains to the west. This sea covered the Great Plains of North America. Can you believe it? The Great Plains were covered by sea, and it ran all the way from Alaska to the Gulf of Mexico. Shallow marine sediments deposited in the sea are exposed in the cliffs and slopes of Mount Everest, visible from Mammoth. And let's take a look at that together. Right, this is the Great Plains, as we can see from Alaska all the way down to the Gulf of Mexico. This would have been an area of the sea. Look at that. The Great Plains, the whole area would have been under sea. That's amazing. That's the first time I've ever heard of this. Going back to the Caldera Chronicles. Okay, this is the Mount Everest shallow sea sedimentary rock, as we can see here. from the Cretaceous period are the overlain by the Huckleberry Ridge Tuff volcanic deposit from the first caldera-forming eruption of Yellowstone hotspot 2.1 million years ago. And this is how huge it is. These are people up there on the top, hikers on the mountain, and that's the valley down below. Orogeny everywhere. Amazing. So there was a sea flowing through here. Late in the Mesozoic era, sea levels rose again, and the Yellowstone region became part of the shallow sea at the foot of the mountains to the west. The sea covered the Great Plains of North America and ran all the way from Alaska to the Gulf of Mexico. This is astonishing. From Alaska here, all of this was sea to the Gulf of Mexico. Amazing. Okay. And even before the end of the Sevier orogeny, another sequence of mountain building occurred in the region, the Laramide orogeny, 80 to 45 million years ago. Not only deformed sedimentary rocks near the surface, but also reached deep into the Precambrian, that's older than 541 million years ago, half a billion years ago. The Precambrian basement, bringing these rocks up to the surface along faults. These basement rocks are 2.7 billion years old. That's half of the age of the Earth, as we said, and very resistant to erosion. You can see them in the steep walls of the Lamar Canyon near Lamar Valley. Yellowstone during this time might have looked like the Andes mountain range. Early in the Cenozoic era, 66 million years ago to the present, that's from the time of the dinosaur asteroid strike, things started heating up with the inception of the Absaroka volcanic field in the Yellowstone region. This volcanic activity was similar to what we see today in the Cascadia Range of Washington, Oregon, and Northern California. Massive flows of ash, mud, and debris buried trees, which became petrified wood. Some of these deposits are preserved in the northern part of the park, for example, petrified forests found on Specimen Ridge. And maybe we have an image here, let's see. The petrified forest of Yellowstone's distant volcanic past, found in rocks and trees. This is one of the beautiful pictures of Yellowstone here. Yellowstone renowned for the largest volcanoes in the world, generating intense interest. The image seen 50 million years ago during the Eocene epoch, climate was much warmer, dense forests of subtropical and temperate trees covered the lowlands. Out of these forests emerged several magnificent stratovolcanoes resembling Mount Rainier and Mount Hood in the Cascade Range. Moving higher in elevation up the flanks of these volcanoes, the forest composition changed to coniferous trees and then to stunted alpine vegetation. At the summits, vegetation gave way to thick fields of snow and ice. And here we have a beautiful petrified tree. Look at this. And that's pretty big, don't you think? An upright petrified tree in Yellowstone Park. That's pretty big. That is pretty big. If that's the trunk of the tree, that's how huge it is compared to the other ones down below, you can see. I can imagine how tall this thing was. Amazing. Petrified tree it does not give us the size of it, but obviously it looks huge. It must have been huge. I mean, you could fit a chair in there, in the middle of it. Let's put it that way. That's how big it was. Yes, millions of years ago. The logs floating in Spirit Lake near Spirit Lake Gauging Station, outflow tunnel. So today, park visitors can observe ample evidence of the Absaroka volcanoes. Fantastic example of the upright tree found. Okay, that's from that era. Amazing. Petrified trees of Yellowstone, remarkable for several reasons. First is the sheer volume. It's one of the largest deposits of petrified wood found anywhere in the world. Second is the diversity of tree species, including spruce, pine, cedar, oak, cypress, ash, dogwood, magnolia, and more. And magnolia, I know, grows in areas that are not don't freeze. So, okay, maybe that's from that time. It was subtropical. This diversity represents an array of ancient trees that inhabited the lowlands and up the flanks of the Absaroka volcanoes. Third is the fact that many of these petrified trees are upright rather than lying on the ground. Some trees were buried upright where they grew, while others were transported downslope in debris flows and eventually settled vertically with their roots wad behind them. Their root wad behind them. Okay. Today, park visitors can observe ample evidence of the Absaroka volcanoes, a fantastic example of upright tree found in just west Tower Junction. Follow the sign for petrified tree. Amazing. Amazing. That's beautiful. So there's a lot to see there. I don't know if they have enough guides to tell the people, inform the people what they're seeing, but hopefully they have some kind of a book or some kind of a tape that people can listen to as they're going to various areas here. So, the petrified wood, we talked about the severe orogeny and the Andes Mountain, that what it looked like, and the Cenozoic era, and the petrified forests. And more recently, starting 16.5 million years ago, a plume of hot material sourced deep within the earth created a hotspot that migrated to Yellowstone due to plate movement, forming the volcanic system we now know today that encompasses most of the national park. Yellowstone isn't always a land of fire, but also experienced two recent periods, about 150,000 to 130,000 and 22,000 to 13,000 years ago, of glaciation. 13,000 years ago, that was the Younger Dryas. Glaciation that reshaped and carved much of the mountains and valleys into their current forms, and that also left mounds of gravel and dropped boulders, like one of these, in odd places as the ice melted. One place to see these deposits is in Hayden Valley, but evidence of glaciation can be found all over the greater Yellowstone area. And this huge boulder, amazing, the trees have grown around it, Glacier Boulder, dropped by a retreating glacier in the north rim of the Grand Canyon of Yellowstone in Yellowstone National Park, and it's a statement of Yellowstone's icy past. That is huge. That is huge. Yes. Now, Yellowstone's youngest rocks are formed by hydrothermal activity. Hydrothermal waters transformed the hard lava flows into colorful clays that erode easily and form the dramatic walls of the Grand Canyon of Yellowstone. At Mammoth Hot Springs, warm water springs deposit travertine that forms terraces. In the geyser basins, boiling water and hot steam erupt from underground pipe-like systems and deposit the silica-rich sinter that forms the cones of our favorite geysers like Old Faithful. So the next time you visit Yellowstone, remember that the big volcanic explosions are just one part of a long and complex geological history, a history that is recorded by rocks that are exposed across the landscapes, spans eons, and tells an amazing story. Amazing. The most amazing story I found out today was the fact that there was a sea between Alaska and Gulf of Mexico, right there. It looks over the Great Plains. All this was an inland sea taking over and covering. That's Yellowstone right there. Right there. Okay. That's amazing. So this is on Caldera Chronicles, and I'll leave a link below for you for this.